If you've ever worked with data in Python, you're standing on the shoulders of an absolute giant. And in this explainer, we're going to dig into the fundamental building block of the entire data science world, the NumPy array. Let's get right into it. So you might be wondering, why do we even need NumPy? I mean, we have Python lists, right? Well, the thing is, lists are fantastic for general purpose stuff. They can hold anything. But when it comes to doing heavy-duty math on huge data sets, they just can't keep up. They're slow. That's where NumPy arrays come in. They were built from the ground up for one thing and one thing only, screaming fast numerical calculations. They're fast, they're efficient with memory, and they are the absolute bedrock of modern data science. And the hero of our story is this thing right here, the ND array, which just stands for n-dimensional array. Now, the definition on this slide is actually the secret to its power. It's not just a collection of numbers. It's a grid of elements that are all the same type, all sitting right next to each other in a continuous block of memory. Because everything is so orderly, NumPy can just skip all the slow, careful checks Python usually has to do and unleash highly optimized C code to do the math at lightning speed. To really get a feel for this, we're going to go on a little builder's journey. First, we'll meet the ND array and check out its blueprint. Then, we'll see how to lay our first bricks by turning lists into arrays. After that, we'll check out the power tools in the creation toolkit, understand its broadcasting superpower, and finally, learn how to get the exact data we need out of our structures. Okay, let's start at the beginning. It's time to meet the ND array. What are the core properties that actually make this thing tick? So every single ND array has a set of attributes that are kind of like its spec sheet. NDim tells you how many dimensions it has. Is it a line, a square, a cube? Shape tells you how long it is in each of those dimensions. Size is just the total number of elements. And dtype is what kind of data is inside, like integers or decimals. But the real secret sauce, the magic, is strides. This tells NumPy exactly how many bytes to jump in memory to get to the next element. It's a super clever trick that lets NumPy do things like flip a giant matrix instantly, without actually moving a single piece of data around. All right, we've seen the blueprint. Now, let's start building. And the most natural place to start is by taking something we all know and love, a plain old Python list, and turning it into an array. And you know what? It's incredibly simple. You just take your Python list, which can be a bit loose and flexible, and you feed it into the np.array function. What comes out the other side is a rigid, highly structured ND array that's ready for high-speed action. A simple list becomes a 1D array, and if you have a list of lists, like you see here, NumPy intelligently creates a 2D array, or a matrix. Now, converting lists is great for getting started, but when you're doing serious work, you need power tools. And NumPy gives you a whole workshop full of functions to create arrays instantly, so you don't have to type them all out by hand. Let's just look at a few of the essentials here. A range is basically Python's range, but it spits out a NumPy array. Super handy. Linspace is awesome for when you know you need, say, exactly 5 points between 0 and 10. And then you've got these workhorses, zeros, ones, and I. They let you instantly pop out arrays of any shape you want, filled with zeros, ones, or an identity matrix. Trust me, these are huge time savers. Okay, so we've built our arrays, but now we get to the really good part. Why is this all so ridiculously fast? Well, it comes down to a couple of key ideas, and the first one is a legitimate superpower. It's called broadcasting. But wait, before we can talk about broadcasting, we have to talk about vectorization. It sounds complicated, but it's not. It just means that instead of looping through an array one element at a time, you apply the operation to the entire array at once. A Python for loop is slow because it has to think about every single step. NumPy doesn't do that. When you type array times 2, you're kicking off a single, highly optimized operation in C code. It is literally the difference between building a car by hand, piece by piece, and having a fully automated factory line do it for you. So vectorization is great, but what happens when you want to do math on two arrays that don't have the exact same shape? That's where broadcasting comes in. It's basically a clever set of rules that lets NumPy handle these mismatched shapes in a really smart and efficient way. Which leads us to a really important question. If we have a giant array with 1 million elements, and we just want to add the number 5 to it, does NumPy have to create a second million-element array filled with the number 5 just to do the math? I mean, that would be a crazy waste of memory, right? And the answer is no. This is the genius of broadcasting. Look at how that smaller array is being virtually stretched to match the bigger one. And the key word here is virtual. NumPy isn't actually making copies of the data. It's just pretending. It reuses the value from the smaller array over and over again during the calculation. This is why it's not just fast, but also incredibly memory efficient. So it's not really magic. It actually follows a really simple and elegant set of rules. First, NumPy lines up the arrays. Then it checks each dimension to see if they're compatible. And the rule is simple. Dimensions are compatible if they're the same size or if one of them has a size of 1. If every dimension checks out, the operation goes ahead. If not, you get an error. That's it. So we've built our arrays. We know how they work their magic. Now we need to figure out how to get our data back out of them with, surgical precision. For a simple 1D array, this is going to feel very familiar. It works just like slicing a Python list with that same start, stop, step syntax we all know. It's a really easy way to grab a chunk of elements from your array.
But here's where things get really powerful. With multidimensional arrays, you just add a comma. You can provide a slice for the rows and another slice for the columns. In one clean line of code, you can carve out an entire subsection of your matrix. This is something you'll use all the time when you're cleaning and exploring data.
Okay, but what if the elements you want aren't in a nice, neat block? What if they're scattered all over the place? For that, we have a technique called fancy indexing. Instead of a slice, you just pass in a list or an array of the exact indices you want to grab. As you can see, this lets you pull out very specific, non-adjacent elements and mash them together into a new array. This is a complete game changer for complex data selection. So let's just do a quick recap. What are the big takeaways here? First, Python lists are for general stuff, and arrays are for speed. Second, NumPy gives you a whole toolkit to create arrays without the hassle. Third, the secrets to its performance are vectorization and that broadcasting superpower. And finally, slicing and fancy indexing give you total fine-grained control over your data. Look, the NumPy array isn't just another data structure. It is the fundamental brick that everything else, pandas, SciPy, scikit-learn, all of it, is built on top of. So now that you understand how the foundation is laid, the real question is, what are you going to build?